Hi guys, we are going to do some combustion analysis problems, two of them today. And first of all, what is combustion? And combustion is basically when we react something with oxygen to form a large amount of heat and light, and the two primary products are water and carbon dioxide. And a combustion reaction usually looks like this. This is a hydrocarbon. It's usually a hydrocarbon that reacts with oxygen to make water and carbon dioxide. So when we have these combustion analysis problems, you'll see they always talk about forming carbon dioxide and forming water, and we can basically use mole-to-mole ratios to track backwards and find out how much hydrogen, how much carbon, or how much oxygen was produced from the water and the carbon dioxide. Let's start with this one right here that says a combustion analysis of a hydrocarbon produces 33 grams of CO2, 13.51 grams of water. Calculate the empirical formula. So I'm going to just write this out here. So if you remember from my hydrocarbon equation I just wrote, that looks like this. We know our products of combustion are water and carbon dioxide that it gives us here. And we can find the product of this hydrocarbon by tracking backwards from the amount of CO2 and H2O produced. First of all, we can do a little mole-to-mole ratio here. We want to get into moles of CO2, like always. The molar mass of CO2 is just adding together the mass of carbon, the mass of oxygen, and the mass of oxygen again, which is 12 grams per mole plus 16 grams per mole plus 16 grams per mole, which is the total molar mass there. This is grams, and then 1 mole. And this is CO2. We can do a mole-to-mole ratio here, and we can see that for every 1 mole of CO2, we are having 1 mole of carbon here. It's a 1-to-1 mole ratio. In CO2, there are 2 oxygens, there's 1 carbon, so 1-to-1 mole ratio for CO2 to carbon. And then this cancels out, and we obviously have our moles of carbon, and that should come out to be 0.75 moles of carbon. For H2O right here, we can do the same thing, the molar mass of H2O is 1 plus 1 plus 16 grams per mole. From the hydrogen are the 1s, and then the oxygen is the 16 right there. And then 1 mole. And H2O, if we're doing the mole-to-mole ratio, we have 2 moles of hydrogen per 1 mole of oxygen. So for every 1 mole of H2O, we're tracking backwards to get hydrogen here. We have 1 mole of hydrogen. And we should get 1.50 mole of hydrogen. If we divide, again, by the lowest amount of moles that we always do for empirical formula, we're dividing by 0.75. And we are getting an answer of 1 mole of carbon and 2 moles of hydrogen. And our answer ends up being CH2. Pretty straightforward. Let's look at another example that involves oxygen as well. So we can have a combustion analysis of a hydrocarbon, like I mentioned, but we can also have a combustion analysis with oxygen as well. And again, it's reacting with oxygen like usual to produce water and carbon dioxide here. It's saying that we have a 16.01 grams of carbon dioxide and 4.37 grams of water. So we know that we can track back like usual from the CO2 right here and find how much carbon. We can track back from the water to find how much hydrogen. We can't use the carbon dioxide or the water to track back and find how much oxygen. We can only use subtraction to do that. And I will show you what I mean by that in a second. But again, let's track back to see how much carbon we have, because we're trying to find the molecular formula here. And we know that to find the molecular formula, we need to find the empirical formula first. So write that out.